All right, hello everyone. This is part 2 of Magnetism, and we're back this week to finish this chapter before we move on to induction next week. And we went through the first half last week, and I explained that I did that on purpose so that we could focus on the first half, which is the magnetic force acting on a current or a moving charge. And then the second half today is a magnetic field created by a current. How do I determine the magnitude and direction of a magnetic field created by a current using either Ampere's law or Biot-Savart? Now, Ampere's law, like everybody agrees, that will be on midterm 2. Whether you have Bordel or Spelio, it doesn't matter. Biot-Savart, however, it's a question mark, sort of. I mean, I've heard from at least 3-4 students that have Bordel that Biot-Savart will not be on midterm 2, so you're not responsible for it. I have not heard the same from Spelio students, and who knows what he might decide to put on there. So most of what we're going to do today is Ampere's law, but I will throw in a tiny bit of Biot-Savart in there at the end, just as an insurance policy, which basically means that if I do talk about it, then it's not on the midterm, but if I don't, then of course it will be. So as a matter of insurance, we'll just do a little bit of Biot-Savart so that you can see how it works and how you might set it up. And we'll do the most common case, which is the semicircle of current. So that's the goal for today. Macro, what we're doing is we are looking for the magnetic field created by a current. And there's two methods, Ampere's law and Biot-Savart. Ampere's law being the main one that we're going to use. And Ampere's law has similarities with Gauss's law. So in spirit, it's the same idea as Gauss's law. Mathematically, it is something very different that you are doing, but you'll see that the way that you apply the math is reminiscent of Gauss's law. So we'll start with that, and we'll try to do a quick recap to explain Ampere's law, at least in basically simple terms, let's say, and of course what's really going to help is to see it applied. But Ampere's law is a method to find the magnetic field created by a current distribution that has enough symmetry. Okay, so the requirement is the same as Gauss's law, where we needed high symmetry. Here it's going to be the same. We're going to need high symmetry to apply Ampere's law. And it'll work for infinite wires or cylinders, infinite slabs or sheets, solenoids and toroids. And I'm going to do basically an infinite cylinder with an inner core and an outer cylindrical shell to see how we would apply Ampere's law to that. But in general, what we're saying is that, well, let's imagine that we have a region somewhere in space where there is a magnetic field. And humor me, because I have to start by drawing something. But let's say that we have a closed contour, right? And that there is a magnetic field everywhere in space. Maybe this magnetic field is counterclockwise overall. Okay, but we're not exactly sure what it looks like, what the field lines look like. They don't have to be circular. But everywhere I look, I have a magnetic field kind of like this. Okay, and maybe sometimes it's at a certain angle from this contour, and that angle changes. But I have a magnetic field. Now, presumably, there's got to be a current or something to create that magnetic field, because there's two ways to create a magnetic field. Or you get a permanent magnet, okay, and you can use that. But what we're going to focus on is magnetic fields created by currents, because, well, you can control what you get a little better than with a magnet. I mean, if you want a specific type of magnetic field in terms of direction or strength or both, it'd be easier to use a current. So there's this magnetic field. Let's say we're not sure where it comes from, but maybe, by the right-hand rule, there's probably at least a current coming out of the page, right? Because if I wrap my fingers around counterclockwise, my thumb points out of the page. And so I would suspect that maybe there's a current coming in like this through the back of this thing and then coming out toward me. Maybe that's I1. But just to be general, we'll allow there to be maybe a current I2 that pokes through this thing and comes out this way. This would be I2. And what we're going to do is we're going to take this contour and we're going to give it an orientation. And when we say give it an orientation, we mean we're going to give it a little direction, well, an overall direction, which is counterclockwise. And at each little point here, where the magnetic field is tangent to the contour, I'm going to have dl like this. And depending on where I am, the angle between B and dl, which is theta, is going to change. And it'll be bigger or smaller, probably. It just depends. And the question might be, well, wait, what are we doing and why are we doing it? Now, first of all, let's be clear. This drawing is not helpful in practice, as in you will never have a contour that ugly and currents that are weird like that to account for in a problem, because this just doesn't make sense. This is the most abstract drawing I can draw to illustrate Ampere's law. And you might say, well, why would you do such a thing? Why do you make your drawing so abstract? Well, the point of a drawing in physics, because typically a drawing goes with a formula, is to reference everything that shows up in the formula so that you know, for a more concrete case, how to draw all the different parts that you need to apply Ampere's law. So the drawing here is not meant to be helpful. It's just meant to illustrate the quantities that show up in Ampere's law. And then we'll see how to apply it in a more practical case. But the idea is the following. Let's say we have a certain current, maybe a combination of I1 and I2. Maybe let's say I1 is stronger than I2. That's why the magnetic field overall tends to be going counterclockwise, because if I have a net current out of the page, B goes around counterclockwise. And I show up and I say, well, I would like to evaluate what B is equal to, ideally. And there's already the current and there's already the magnetic field, that already exists. What I'm going to do is I'm going to take a closed contour. This is called an Amperian contour. And I'm going to place it on the problem. And I'm going to determine how much of B lies along my contour. Now this is similar again in spirit to Gauss's law. If you remember in Gauss's law, we would take a closed surface, typically a sphere or a cylinder. We would put it on the problem and we would say, well, the flux through this imaginary mathematical surface is equal to Q enclosed over epsilon naught. And then it's simplified and we found E. Well, Ampere's law is the same idea, except it's not a surface, it's a contour. So it's a closed loop, right? And then we give the loop an orientation, and then we're going to say, well, we're going to compute at every point B dot dl, which of course, again, with my drawing is incredibly complicated, but in practice is going to be very straightforward. And this is going to be how much of B lies along dl. That's the definition of a dot product. It measures A dot B measures how much of A is along B. And so what you're saying is, okay, well, how much of the magnetic field goes around my contour? That has to be related somehow to the current that I encircle, because after all, the current that I encircle is what created B in the first place. Now, B dot dl is just for one location on the contour. If I want to account for the entire thing, I have to integrate over a closed contour, so I'll put a ring on the integral to indicate that the contour is closed, and I'll say that that's equal to mu naught times I encircled. Okay, so very similar again to Gauss's law, even in format. Now, mathematically, it's something very different. This is not a flux, right? This is called a circulation of B. So it's not a flux, has nothing to do with the integral of E dot dA, but it's still equal to some, instead of Q enclosed over epsilon naught, it's mu naught times I encircled. So it seems to have a very similar right-hand side. Now the question then is, how much is I encircled? Okay, how do I define I encircled? Okay, now to do that, and we might revisit this later on, it depends if we get to Ampere-Maxwell this semester or not, but for now, in the case of Ampere's law, what we're going to do is say that this contour here, this closed Amperian contour, bounds a surface, which is this surface, right? It's the boundary of this surface here, right? You could imagine if the black contour were a piece of metal wire and I dump it into soapy water, right? And I pull it out and I have a soap film across it, that's my blue surface, okay? And any current that goes through that blue surface counts as an encircled current. So I1, for instance, counts as an encircled current because it goes through this surface right here. Same thing for I2, it goes through the surface right there. Now maybe I have, I don't know, I3 out here. Well, I3 is not encircled, and so we don't care. All the same that we didn't care about charge that was not enclosed when we talked about Gauss's law. Only the enclosed charge mattered. So currents that are outside of that surface that do not flow through it do not count, but I1 and I2 are encircled currents and they do count. Now they go in different directions, so now I have to decide is there one that's positive, one that's negative, and how do I know? Well, overall, my B is counterclockwise. Therefore, I have to match the right-hand rule. If B is going counterclockwise, then current coming out of the page is going to count positive. In other words, if I claim that counterclockwise is positive for B, for field lines, then I have to match it with current coming out of the page is positive by the right-hand rule. So I encircled is going to be equal to, well, I1 is going to count positive because it comes out of the page through the surface, but then I2 is going to count negative because it goes into the page. Okay. Now, a lot of the time there's only one current, so I have to worry about plus or minus, but this is how I would decide which one is plus and which one is minus. Okay. And so this is what Ampere's law says. Now, all the same that Gauss's law didn't tell you anything if you couldn't simplify it, well, Ampere's law doesn't tell you anything if you can't simplify it. I don't actually care what this is equal to. What I care is to have B that is constant in magnitude and direction along my contour so that I can simplify the integral. And that means that part of the art is going to be choosing a contour that does that well. You'll find that it's either circles or rectangles for 8B that gets the job done every time. And how you decide depends on what the magnetic field looks like. But the condition here is that if B is constant in magnitude and direction on the contour C, then the integral of B dot dl, which, by the way, by definition of the dot product, which you already know, is B cosine of theta, the angle between B and dl times dl, is going to be something that simplifies because B and theta are constant on the contour, they get pulled out, and dl is the little piece of length of my contour. Well, if I integrate just dl all around my closed contour, guess what I get? I get the length of my closed contour. So that'd be BL cosine of theta. So of course, in practice, it means that I have to have a reasonable contour. At minimum, because I need to find the length of it. So what's the length of this thing? I don't know. I'm not finding it, no. But again, this is an abstract drawing just to illustrate what shows up in Ampere's law. And we're going to find that in practice, our Amperian contours are going to be circles, for which it's easy to find the perimeter, or rectangles, same thing. And therefore, it's very easy to both compute I encircled and the integral of B dot dl. And then we can find B, because again, the goal is not to figure out what this is equal to. I could not care less what that quantity is. I simply care that it breaks down so that it gives me access to B. I want to get my hands on B because my goal is to find the magnetic field created by the current. Okay, so with that said, let's go have a look at an example here where we have a hollow cylindrical conductor and we have a certain amount of current flowing through this cylindrical ring. I think I said at the beginning that I was going to do one with a core here, a solid core in the center. You can have one or not. I guess there is none. I did not, I didn't remember that correctly. But the point is, you'll find this problem or similar problems everywhere, right? You could have a wire of current here, like that, and you could have a cylindrical core with a certain radius and a certain current, and so forth, and then an outer cylindrical shell like here. So I'm going to solve it like this first, and then at the end what we'll do is we'll add a wire with a current, maybe going in the other direction, just to see what changes if we had an additional current somewhere in the center. But this is going to be a geometry, a shape that is conducive to applying Ampere's law. How do I know? Well, I need enough symmetry, but even simpler, I know that Ampere's law applies for infinite wires or cylinders. They could be hollow cylinders, it doesn't matter. Infinite sheets or slabs, the solenoid and the toroid. So if I don't have one of those, it's not going to be Ampere's law. But here I do have a long hollow cylindrical conductor that's, okay, it's long, so presumably long enough for infinite. We know the radii and we know the current per area J. And we want to find the magnetic field in the three different regions. This is also reminiscent of Gauss's law, where the three different regions are region 1, region 2, and region 3. Okay. Now, before we do that, let's just agree that because of the current coming out of the page, I expect that my field lines are going to be circular because of the symmetry and counterclockwise by the right-hand rule. My thumb out of the page, wrap my fingers around my thumb. I anticipate that B is going to be counterclockwise where B exists. Maybe there is no B in some region, but wherever B exists, there will be a counterclockwise orientation to the field lines. So then we can redraw this maybe real quick just to have it, right? So this, I'll make a copy of this here. There we go. And then we'll bring that down here. And we'll apply Ampere's law 3 times because we have 3 regions. Okay. And, well, perhaps just to make things clear, we should indicate that this is a solid region. So it's the inside that's hollow. So this is where the conducting material is through which there's current flowing out of the page. Okay. So actually, let me just there we go. Do something like that and then make a copy. All right. So let's start with region 1. Region 1 is for little r smaller than A. Right? So it's within the hollow part of this cylinder. And I have current per area J coming out of the page, but within region 2. So there's nothing within region 1. Now, if you are already pretty comfortable with Ampere's law, you'll probably conclude immediately that, well, region 1 has no current, so I'm going to find B1 is equal to 0 eventually because I encircled is going to be 0, which is true. But if you don't know that already, then let's just play along and say, okay, well, given the shape, I expect my field lines to be circular, and given that current comes out of the page, I expect them to be counterclockwise. So let me draw field lines like this for B1 that are going to be circular and counterclockwise. Now the goal of Ampere's law, based on what we just talked about, is to say you have a current and you have B, and you want to solve for B, and the way you do it is you put a contour, which is a closed contour, onto your problem to analyze it and solve for B. And the closed contours are going to be circles or rectangles. That'll get the job done for any distribution in 8B. And I decide based on what the magnetic field looks like. And so B1 is a circular field line. I'm going to choose a closed contour that follows B1 as much as possible, and that would be a circle. So I'm going to choose a closed contour here that's going to be a circle, and I'm going to make sure that it follows B1. It's going to have a radius little r, which is going to be less than a, an orientation dl, which is going to be counterclockwise so that I follow B1. And what I get to do now is say, well, the integral of B1 dot dl around the closed contour is equal to the integral around the closed contour of B1 cosine of the angle between B1 and dl, which is 0, because then they're in the same direction. And then B1, of course, by symmetry, is the same everywhere around my green contour, because well, it wouldn't make sense to have a stronger magnetic field here than here than here. After all, every point of the green contour is the same distance from the center. So by symmetry, B1 is constant over the entire contour, and cosine of 0 is 1. So I'm going to get B1 multiplied by the integral around the contour of dl. dl is a little piece of length or arc length. If I integrate that all around, I'm going to get the circumference of the circle. That will be B1 2 pi r. Okay. So again, similar to Gauss's law, which ended up giving us flux, which is E times area, here we get B times length. Okay, so mathematically we're doing things that are very different, but the process really mirrors what we used to do in Gauss's law. So then the question is, how much current is encircled in my Gaussian, in my Amperian contour, or by my Amperian contour, I should say. Well, my Amperian contour defines an area, like a surface, like this, and any current flowing through that surface counts as an encircled current. And if it flows out, it'll count positive. If it flows in, it'll count negative. And if there's none, like here, then mu naught I encircled is 0. All right. And so by Ampere's law, we're going to have B1 2 pi r is equal to 0, which of course leads to B1 is equal to 0 in region 1. And so, same idea as Gauss's law. When we had no charge enclosed, we came to the conclusion that E was 0. Well then, with no current encircled, we come to the conclusion that B1 is 0. Okay, now what happens if I move to region 2? Okay, let's maybe move this up so we have a little bit more room. And I'm going to have region 2. That's going to be for R between A and B. And by the way, because of the shape, I expect that B2 is going to have circular field lines. They're going to be counterclockwise, so that's going to be B2. And the same thing is going to take place again. I'm going to choose a closed contour that follows B2 as much as possible, and then that's going to have a radius little r and an orientation dl, which is counterclockwise. Now, if I do that, the integral, which is the integral around my closed contour of B2 dot dl, does not know the difference between what I just drew and what I had before. All it knows is that we're following B, whether it's B1 or B2, around a circle of radius little r. And that's all it cares about. And so I'm going to get the same circulation of B. There's no reason for it to be any different. It's going to be, with the same simplifications, just with B2 instead of B1, I get B2 2 pi r. Okay, well, with that said, then what does change? Well, just like when you go from region to region with Gauss's law, the enclosed charge changes. Here, when you go from region to region with Ampere's law, the encircled current changes. So how much encircled current do I have? Well, as a reminder, I have current coming out of the page everywhere in the conducting cylindrical shell, right, to the tune of J, that's current per area, but I only care about the encircled current. So yes, I also have current coming out of the page out here, I just don't care about it. I only care about what's encircled. Now, how much is encircled by my contour? Well, that would be how much flows through the surface bounded by my contour. And so mu naught I encircled is going to be equal to mu naught times J, which is current per area. Just have to be careful with the area. This is the area we want. We just want the area of this little ring there. Okay, now that's going to be pi little r squared minus pi a squared. Okay, so this is going to be mu naught pi j times r squared minus a squared. And then by Ampere's law, I'm going to get B2 times 2 pi r is equal to mu naught pi j r squared minus a squared. Pi goes away, but I get B2 is equal to mu naught j over 2r little r squared minus little a squared. And that's going to be in region 2, which is for r stuck between A and B. All right. So that's how much, or that's what, rather, the magnetic field is going to be in that region all the way up to the edge of the cylindrical shell. Okay? And by the way, we know that it is counterclockwise. So if you want to indicate direction of the magnetic field, of course, you can always just write counterclockwise. Everybody will understand. If you want to do it with vectors, or you might see it written with vectors, then you'll find that it's vector B2, and then the vector that says that means counterclockwise is theta hat. R hat means radially outward, theta hat means counterclockwise. And so if you write theta hat, everybody will understand what you mean. So this stands for counterclockwise. All right, so now we have B2. Fair enough, we can move on to region 3, which would be outside of the whole thing. All right, region 3 is going to be the region for which r is greater than b. Same thing as before, right? I have a shape that leads me to conclude that the magnetic field lines are going to be circular. They're going to be counterclockwise because all the current is coming out of the page. And then I'm going to draw a closed contour, which is going to be a circle here, that is going to follow B2 as much as possible. It's going to have a radius little r, an orientation dl, and same as the previous two regions, the integral over this closed contour of b3 dot dl is going to be equal to b3 times 2 pi r. All right. To be equated to mu naught I encircled, and therefore we have to figure out how much current is encircled. Okay, well, again, I have J, current per area, coming out of the page through the thickness of this cylindrical shell, right, through the wall of this cylindrical shell. But of course, I now encircle all of that shell. So I need to take J and I need to multiply it by the round amount of area. But I have to be careful, I don't want to overcount. It only matters what the cross-sectional area of the conducting material is. In other words, the only area that matters is the area of this ring here, right? The whole thing, for that matter, but not anything in here or not anything in between the cylindrical shell and the gap, or within the gap between the cylindrical shell and my Amperian contour, all right? So I'm just going to have mu naught J times, it's going to be pi, hold on, there we go. It's going to be pi b squared minus pi a squared here. So that's going to be mu naught pi j b squared minus a squared. By Ampere's law, these two quantities are equal to each other, and we find B3. So B3 times 2 pi r is equal to mu naught j pi b squared minus a squared. Pi goes away, and we conclude that B3 is equal to mu naught j divided by 2r times b squared minus a squared. That's for r greater than b, and that will be a counterclockwise magnetic field. All right. So I was just going to say very straightforward to apply Ampere's law. Maybe that's not fair. Very straightforward if we recognize that there are similarities in the process between Gauss's law and Ampere's law. Well, the only thing to keep in mind, again, and I know I'm beating a dead horse here, but it's just that mathematically we're not doing the same thing at all. One is electric flux, which is equal to charge over epsilon naught. The other one is magnetic field circulation, which is equal to mu naught times encircled currents. So mathematically it's very different, but the process kind of unfolds in similar ways. And in both cases, it only matters what's either enclosed or encircled, so that is also another similarity. Now, I had said that before finishing this problem, I would do a variation of it where maybe we could add a wire in the center that carries a current going back into the page. So let's do that. Let's do a variation, only because these types of problems are super common. And it's always nice to see what changes if you just change one thing. Okay, so let me do this. I'm going to get rid of B1 and all that. I'll color this back in just so that we understand where the current is. Right, it flows through this conducting material here. There we go. And now I'm going to have a current, I'm going to call it I0, going into the page. And I could give I0 any value I want. Maybe, just maybe, for the fun of it, I can say that I0 is going to be, I'm going to make it J times pi b squared minus a squared, which I don't have to do. I'm choosing a specific value so that I get an encircled current of 0 once I'm outside of everything. I don't have to do that. I0 could be completely independent of j. It wouldn't matter. Okay, but let's see how things change. So let's go, well, first of all, let me make a few copies of this. Now let's go fish out here what we got for region 1. Just make a copy of it. Okay, so this is for region 1. What changes now that I have a current I0 going into the page? Well, first of all, maybe I have to decide whether B is clockwise or counterclockwise. Before I had I0, it was easy. J came out of the page, so by the right-hand rule, B had no choice but to be counterclockwise. But now I0 goes into the page, so, I mean, then that tends to create a clockwise B. So I will do this. I will say, you know what? Maybe I don't know. Maybe I'm just, I'm not that comfortable yet with Ampere's law, and so I'm not going to try to guess if B is clockwise or counterclockwise. I'm kind of going to close my eyes and pick one and hope for the best. So I'm going to pick the same orientation as before. I'm going to claim, and we'll see what happens, that B1 is still counterclockwise, even though I actually know that it has to be clockwise, because in region 1, you only encircle one current. That current is into the page. Therefore, B1 must be clockwise. But fair enough. Let's just do this. See what happens. Okay. All right. Same thing, right? We can, oops. No, that's not the same thing. There we go. Amperian contour. Radius little r. Okay. DL. All of it. All the same. In fact, so much so that this does not change. It's just B1 times 2 pi r. However, now, I encircled is not 0. I definitely have a current that flows through the surface bounded by my Amperian contour. In fact, I have all of the current I0 that flows through that surface. The question, though, is I0 positive or negative? Now, I just chose B1 to be counterclockwise, so I'm kind of saying positive direction for field lines is counterclockwise. Now I can do that, but then as far as sign conventions go, I have to match the right-hand rule. So if I say that B1 is counterclockwise, even though I might be wrong, then it only makes sense to associate out of the page as positive for current, because that's what the right-hand rule tells me. If I wrap my fingers counterclockwise, my thumb points out of the page, so a positive current would be a current that flows through that surface out of the page. Well, this one does not. It flows through the surface into the page. So it's really going to be mu naught times minus I0, in other words, minus mu naught I0. Okay, and so by Ampere's law, we come to the conclusion that B1 is going to be equal to minus mu naught I0 divided by 2 pi r. So it'd be for r less than a. Now the minus sign is Ampere's law self-correcting. It said, well, John, you decided to go with B1 counterclockwise. You closed your eyes and you're like, okay, hope for the best. But then you had to say that I0 is actually a negative encircled current because into the page is associated with clockwise and not with counterclockwise. And so therefore, I am doing you a favor, as Ampere's law. I am course correcting and putting a minus here that tells you that B1 is actually clockwise. Okay, the minus tells you that whatever I guessed for B1 in terms of direction is incorrect. Now, the magnitude is going to be this. That's fine. There's nothing wrong with that. It's just the minus tells me, well, okay, B1 just goes the other way, actually. Okay. Okay, so then, well, region 2. Okay, we're going to do the same thing. I'm going to need more room than that. Hold on. Let me, got a housing crisis going on here. Let's, there we go. Okay, so let's do the same thing. Let's just say, okay, region 2, let's choose B. Well, clockwise or counterclockwise? You could say, well, now I actually know that it's clockwise in this region. But now I enter the blue region, and now I have a current out of the page that kind of compensates the current into the page. And like, darn it, I still don't know. I'm not sure. I mean, it depends how big out of the page is versus into the page. Don't know. So again, it's okay. We're going to guess. We're going to guess, and math is going to course correct if we're wrong. So I'm going to keep on guessing that B2 is counterclockwise. Okay. I'm going to choose an Amperian contour. It's going to be a circle of radius little r. Well, let's try for a circle. There we go. A circle of radius little r that is going to follow B2 as much as possible with a counterclockwise orientation. This is dl. And I'm going to go fish out what we found earlier, which was this. Okay, so in region 2, we wrote this. Now, there is no difference between what we wrote before and what we are going to write now when it comes to the integral. And it's still going to be B2 times 2 pi r. The integral doesn't know what region we're in. It just knows that, hey, dl is counterclockwise, B2 is counterclockwise, so, okay, it's going to be B2 2 pi r at the end of the day. However, I encircled is going to be different. So what is I encircled now? Again, as before, I can pick B2 as counterclockwise just as an educated guess. Could be a good guess or a bad guess, but at this point, I've guessed. So if B2 is counterclockwise, and that's positive direction for field lines, I now have to use the right-hand rule and argue that, well, out of the page is the positive direction for current flowing. So I have to stick with that. And I do have some current out of the page, but I also have I0 into the page. So how much encircled current do I have? Well, let's evaluate the current that flows through this surface here. Now, into the page is negative. So that's going to be minus I0 because I encircle all of it. And then the question is, how much current do I have in this tiny region? Should have drawn my circle bigger, but okay. In the tiny part of the blue region, right here, that has current J coming out of the page per unit area. Well, first of all, it's going to be a positive amount of encircled current because it comes out of the page. It's going to be J times the right area. That area is going to be, just like it was before, pi r squared minus pi a squared. Okay? And by Ampere's law, we're going to find that B2 is equal to mu 0 over 2 pi r. It's going to look a little weird, but bear with me. Minus I0 plus J pi r squared minus pi a squared. Okay, well, it is what it is. I mean, that's what I get. Okay. Now, is it counterclockwise or clockwise? Not as obvious as before, right? Like before, I got a minus. That was pretty clear that I was wrong about counterclockwise, and it was clockwise anyway. Well, here I don't know. It depends how much, well, rather it depends how this compares to this. In other words, it depends how big I0 is going into the page versus how big J is coming out of the page. But overall, this is going to work because this is going to be negative, and as long as it's more negative than this, B2 will be negative. If I compute it and I get a negative number, I'll say, oop, JK, it is clockwise, not counterclockwise. But perhaps, depending on what you choose for J, this at some point becomes bigger than this. Then B2 will be positive for that value of R, and if I compute B2 and I get a positive, I say, oh, I guessed correctly. It is counterclockwise for that value of R. So again, the math self-corrects as you go. Right? The same thing happens with Gauss's law, although we never really realize it because the problems that we do, we don't usually have to worry about that too much, but it's the same idea, right? I can guess flux is in or out, or maybe I guess the flux is out, but if I come up with a negative Q enclosed, then I get a negative value for E, and it tells me flux is inward, so E is inward. Okay, so here the sign SIGN of this thing depends on little r. Of course, it depends on how j compares to I0, but if it turns positive, then I conclude that B2 is counterclockwise, and if it comes out negative, then B2 is clockwise. All right. And then the last region, let's just do this to see how we would deal with it. I'm going to say, okay, well, it's the same problem, isn't it? I still don't know if B3 is going to be positive, negative, or potentially 0. I don't know, right? It depends how big this is compared to J multiplied by the blue area. Don't know. If I don't have numbers, I don't know. So again, I'm just going to guess. I'm going to say, oh, B3 counterclockwise, okay, and I'm going to choose my Amperian contour so that it has a radius little r, and it follows B3 as much as possible, so I'll give it a counterclockwise orientation. And then I'm going to go fish out this part that we have here for region 3. All right, bring that down here. And then let's see what changes, okay? So region 3, well, the integral doesn't change at this point. I think we know that. But, of course, I in circle changes. Okay, so what is I in circle? Well, I have mu naught times the following. Well, same as before. I can say, okay, B3 is counterclockwise. I've made my guess. Now I have to match with the right-hand rule the positive direction for current. So if counterclockwise is positive for field lines, my thumb comes out of the page by the right-hand rule. Out of the page is positive for encircled current. And now I encircle all of it, like all the current I0 going into the page, but all the current per area J coming out of the page. So I have to account for all of that stuff. Okay, I just want to be careful with J. I don't want to overcount. I don't want to multiply it by an area that's too big. But this is going to be the surface bounded by my Amperian contour. Current into the page counts negative. This is minus I0. Current out of the page counts positive. That is J multiplied by the proper area, which is the blue area of the cross-sectional area of the conducting cylinder. This is going to be pi b squared minus pi a squared. That's just like what we did earlier. Okay. Well, because I0 is equal to this, which I could have substituted before, I didn't, but I could have, I'm going to find that this is mu 0 multiplied by minus j pi b squared minus a squared plus j pi b squared minus a squared, which is going to be 0. So total, I have the exact same amount of current flowing into the page than out of the page. And so my conclusion is that B3 is going to be 0 for R greater than B. And probably could not have guessed that ahead of time. So it's okay. I still drew B3 counterclockwise. And I said, you know what, we'll find out. Well, we found out. It's not that it's clockwise versus counterclockwise, it's that it's 0. There is no magnetic field. But okay, you know, until you tell me, you know, something like this that I can plug in, then I won't know. So that's how that would change. But the point is, the process is always the same. Okay, you go through it the same way. If you have multiple regions, you apply Ampere's law in each region. I usually go from the inside outward, but you can do whatever you want. And just be careful how you count I encircled, right? And how it compares to the direction of the field lines. You want to get that figured out with the right-hand rule. But there's a lot of problems like this one. And it doesn't have to be just a wire. It could be a conducting cylinder with a radius little r, well, probably not, let's call it little r1 or whatever, so it's not this little r. But point is, you don't have to have a wire in the center. You could have a conducting cylinder or something like that. And it's okay, you just do the same thing. You have one more region. You do Ampere's law 4 times. And you just keep on going. So hopefully that makes sense. how we apply Ampere's law and how it works. It's, it took a little bit of time to accept Gauss's law and to look at it like a good tool to find E and be comfortable with it. And once you're comfortable with it, you can really fly through those problems. Ampere's law is the same way. So it's worth, you kind of hunker down a little bit, spend some time on different problems and see how the different geometries affect the shape of the field lines for the magnetic field. And then how do I choose my contour? Is it going to be a circle or a rectangle? Here, a circle, of course, because we're following B, and the best way to follow B is with a circle. But if you had a sheet or a slab, you would find that B is horizontal above and below the slab, and then a rectangle really gets the job done. Okay, so spend some time with it because it's easy points on an exam. If you know how to apply Ampere's law, it's usually straightforward because it's a repetitive process that if you've practiced enough, even if you have something that you've never seen before, you'll probably be comfortable with it. Or comfortable enough, let's put it that way. All right, so that is for Ampere's law. Now, I do get a funny feeling that if I stopped here, everything would be fine, and I'm going to do Biot-Savart, but it's not going to matter because it won't be on the midterm. But Bordeaux students, again, 3 or 4 of you have told me that there is no Biot-Savart, so that's more or less 100% confirmed. You can confirm for yourself if you want to be sure. Speleo students, I think midterm 1 taught us that anything is fair game, at least in his mind. I would debate what is actually fair game and what isn't, but hey, I don't write the exam, so it doesn't really matter what I think. So as a matter of an insurance policy, call it an umbrella policy, we will do Biot-Savart, so at least you're not completely new to it when you go practice it on other problems or old exams. Okay. So, well, let me do this. Let me insert, no, that's not what I wanted to do at all. I'm going to insert a blank page here so I can write down a few things about Biot-Savart. All right. Now, Ampere's law works really well if you have high symmetry, but as we listed off, there's only so many cases for which you can apply Ampere's law. And that was similar for Gauss's law. There were only certain geometries that worked. So Gauss's law and Ampere's law are very easy to apply, and it's easy to get your hands on E and B, but it requires a high amount of symmetry, which is not guaranteed for all distributions. So particularly here, there are currents that might have a certain shape where Ampere's law just doesn't work. You can't use it. So how do you do it? Well, the other option we had for electric fields was slice and dice, okay? And therefore, there must be an equivalent option for magnetic fields. Now, we could call it slice and dice, but really it's just called Biot-Savart, but it's the same idea. It's just maybe a little bit different than the slice and dice that we did previously, but it's the same idea overall. And we're going to find that if we can just take the right little piece of current on the charge distribution and set up the tiny magnetic field contribution, it's not necessarily that hard to get the whole magnetic field, but I will have to integrate just like slice and dice for E. That is the price to pay. So I'm going to, again, just like I did before, draw a drawing that is absolutely not helpful because it is too abstract. We will never have a case like this to solve. But again, remember that in physics, the goal of the drawing is to reference the quantities in the formula so you know what they are, so that if you go see a problem that is similar, you can set it up with all those little pieces of the puzzle because you can base it off this drawing. So this is a current in a wire. Okay? So this is a wire of current. And we know, this is actually in part what Biot-Savart tells us, is that magnetic field lines encircle the current that gave rise to them. And by the right-hand rule, if I put my thumb along the current and I wrap my fingers around my thumb, then I'm going to get field lines that are going to encircle like this. So I'm going to have B coming around like that, and then going behind the wire. So this is going to be behind the wire, and to make sure that that's super clear, we will make this part a dotted line. Okay, dotted line is behind the page, solid line is coming out of the page, and the magnetic field B is going to look like this. All right. Now, what Biot-Savart does is it slices and dices this thing. So it takes a little piece of current. It's going to take a piece and make a copy of this. It's going to take a little slice, I times dl, and this is a vector. And then at the location of interest, let's say I want to find the magnetic field right here at this point. Well, Biot-Savart is going to tell me how to do that. It's going to tell me how to find dB, the infinitesimal contribution to the magnetic field at that point. Now, Biot-Savart, it is not based on anything physical, meaning that it is just math and it works. That's it. Okay, so it's mu naught I dl cross r hat over 4 pi r squared. Okay, so this is why we need the drawing, because we need to understand what dl is. We need to understand what, this should be r hat is, and what little r is. Okay, so if this is the point of interest where I want to find dB, well, first of all, I know that its direction is going to be into the page, so there's that. But what is little r? Little r is the distance between the base of IDL and the point where I want to find dB. So this is little r. I'll make it a dotted line just so that we're not confused. So that's the distance that I want. That is going to define an angle theta between dl and the dotted line. And at the point of interest, r hat is, there we go, r hat is the vector that points away from the base of IDL. So it's aligned with the dotted line, points away from the base of IDL. That is r hat. Now in theory, r hat's going to tell me, along with dl, that dB is into the page, because dl cross r hat is a cross product, and the right-hand rule applies, as in first vector along my forefinger, that's dl, second finger along, middle finger along the second vector, r hat, my thumb will point into the page, and that's the direction of dB. It's a little tedious to do it that way, so we prefer the wrapping your fingers around your thumb. That's kind of a shortcut to get to the same answer, which is a bit more practical. But the point is that's really why you need r hat. Okay. And of course, to a degree, it defines theta, which you're going to need as well. But so those are the quantities you need. Okay. And you need them because, okay, the magnitude of dB, so dB without a vector in magnitude, is mu naught I dl. Now the magnitude of r hat is 1, so that doesn't matter. And then I'm going to get sine of theta divided by 4 pi little r squared. That's it. Okay, that's kind of the problem, is that when we teach it, we're like, oh, that's it. You're not experts at Biot-Savart, which of course you're not. You have to see it applied to all the cases that work. So the finite wire of current, the semicircle of current, and the ring of current, which are the most classic ones to apply Biot-Savart. And sometimes there's a few others that are that you could encounter, but they're a bit more complicated. So we tend to limit ourselves to those. So, okay, let's go see how we might apply that to a problem. Okay, and oops, no, let me do this. I will, okay, I'm just going to bring all of this with us so that we can reference it down here. here we have a wire of current that is bent into a specific shape. You could think of it as an omega here, right? Overall, this is the shape of a Greek omega with a very tiny gap here, like so small in fact that you can consider it to be the contribution of one long infinite wire and one ring of current. Okay. Now, if I look at this, well, first of all, I know it's not Ampere's law, but it turns out I don't even know how to do it with Biot-Savart in one fell swoop. What I have to do is deconstruct this. I have to say that it is the superposition of an infinite wire, which I actually know how to do that with Ampere's law, and a ring of current, and that's going to be Biot-Savart. So we are going to start with Biot-Savart because that's the whole point, and then the magnetic field created by an infinite wire, I can just use the formula for that. I don't have to prove it by applying Ampere's law. And then we can combine everything at the center. Okay? So let's assume that we want to find the magnetic field at the center of this thing if we just consider this ring of current. Okay? So I need two of these, and you'll see why. Okay, and I want the magnetic field at this point here. All right, and I know that the current is going to go clockwise around this thing. So I'm going to draw, at some location, an arbitrary location, a tiny little IDL, a length dl with a current I clockwise. At the center of the circle, by the right-hand rule, if I wrap my fingers around clockwise, my thumb will point into the page, so I anticipate that B from the semicircle, I'll call it dB semi, is going to point into the page. Okay? I'll put that here for clarity. Now, I need to set up Biot-Savart. So I have my cheat sheet here on the right, and I know that I need to find first the distance between the base of IDL and the point where I want to find the magnetic field, which is the center of this circle. Now that's going to be little r, but of course little r is going to be big R, the radius of the circle itself. Okay, then I want r hat. Well, r hat is the vector that at the location where I want to find dB points away from the base of IDL. And now the angle between dl and r hat is going to be this angle. Well, that's 90 degrees because dl is tangent to the circle and so perpendicular to the radius. All right, so that tells me a lot already. It tells me that dB semi in magnitude, because I already know the direction, is mu naught I dl sine of 90, which is 1, divided by 4 pi, and little r is big R squared. There we go. The only thing that's left is to figure out what dl is. Okay, well, what is dl? This is why I have a separate drawing. Okay, now remember, dl is just a little piece of arc length. I'm going to draw it big enough that we can see what's going on, but if this is an arc length dl, then it subtends an angle d theta. And if this is a radius r, then by definition of an angle in radians, dl is r d theta. But theta has to be in radians. So okay, that tells me what dl is. Fair enough, that's going to be mu naught I r d theta. Sine 90 is 1, divided by 4 pi r squared. Okay, r cancels the square. I get mu naught I over 4 pi r d theta. And just like with slice and dice before, that is just for this little piece of the circular current. I don't know why I called that semi now that I'm sorry, I'm reading this again. It's not a semicircle. It's a circle. Doesn't really matter, I suppose, but dB sub c, let's call it, for circle, whatever. The point is, okay, that this is for one little piece of this circle. I have to integrate over the entire circle to get the contribution from the whole thing at the center. Okay. Which means that, okay, I'm going to integrate over theta, but I should really define what I mean by theta. Now, theta is going to reference the position of IDL, either with respect to the horizontal or the vertical. It's up to you. Now, if it's up to me, I tend to choose the horizontal, but you don't have to. And I'll say, well, you know what? This theta here tells me where IDL is. If you tell me what theta is, I know exactly where I am on the circle. And that means that theta is going to go from 0 all the way around to 2 pi to span the entire circle of current, the entire ring of current. So my bounds on theta are going to be 0 to 2 pi. Okay. Now, if you prefer to define theta with respect to the vertical, you may do so. Right? You could say that this is theta. You're still going to find that theta has to go from 0 to 2 pi to make it all the way around the ring, so it's not going to matter. Okay, so then B, created by the circle of current, or the ring of current, is going to be the integral from 0 to 2 pi of mu naught I 4 pi big R d theta. That's going to be mu naught I divided by 4 pi big R. If I integrate d theta, I get theta. If I apply the bounds, I get 2 pi minus 0. Okay, so this is going to be mu naught I over 2 R. And it's going to be into the page. Okay, so that is the magnetic field created at the center of this ring or this circle of current as derived by Biot-Savart. Okay, so it's actually not very hard to derive. The math is rather straightforward. What's hard to do is to set it up and to understand what to do with this. And that's what requires really a lot of practice when it comes to Biot-Savart. So I found that part. In other words, I've taken care of this. I still need to take care of this infinite wire here. But that's very easy because that's just Ampere's law. Right? So by Ampere's law, if I have an infinite current carrying wire and I want to find the magnetic field at a distance r from the wire like this, well, first of all, by the right-hand rule, I know that this current traveling to the right creates a magnetic field that comes out of the page, right? If I put my finger along I, wrap my finger around my thumb, then I'm going to get out of the page up here. So this is going to be dBW for wire. In fact, it's not dB, it's just BW because I don't need to integrate. I'm just using Ampere's law. And BW coming out of the page is going to have a magnitude that I know. I mean, we could redo the derivation, but it's so common that you're allowed to just say, for an infinite current carrying wire, you're going to get this. It's mu naught I divided by 2 pi little r, which is the distance from the wire, but in this case it's the same as big R. So we found the circle, we found the wire. Now by superposition, we can put everything together. Okay, so by superposition, we have the following. We have the ring of current, the infinite line of current. Technically, it has a tiny little spacing here, but it's so small that we neglected it. And we're saying that, okay, well, if you run a current like this, then B net at the center, well, it's going to depend which one's stronger. It turns out B net is probably going to point into the page because, well, you'll see why. That'll make sense. Right? Remember that B from the circle is mu naught I over 2r versus B from the wire is mu naught I over 2 pi r. So it's smaller than B from the circle. So there's less B coming out of the page than going into the page, so probably B net is into the page. I'm going to choose, I don't know, call it Z hat, the direction into the page. And by superposition, B net is equal to B circle plus B wire. Now as vectors, careful. Now B circle goes into the page, and so it's going to be mu naught I over 2r along Z hat because it's into the page. B wire comes out of the page, so I need a minus mu naught I 2 pi r Z hat. Okay, so you can do one better than that. You can say it's mu naught I divided by 2r multiplied by 1 minus 1 over pi. Z hat. All right, and there we go. That is going to be the magnetic field, the net magnetic field, at the center of this ring of current. So the only part that was Biot-Savart was this part. And again, it's an insurance policy. I did it so that if it is fair game on midterm 2, at least for Speleo students, you have an example of how to apply it. It is well worth figuring out whether or not you're responsible for Biot-Savart if you can. Because if you don't have to worry about it, then great. That's one less thing to learn in the magnetism chapter. You can just focus on Ampere's law, and it just narrows your focus, and it means you can spend more time on Ampere's law and get better at it, or more time on induction, whatever. But the point is, it is worth figuring out whether or not you're responsible for it. But for sure, you will be responsible for Ampere's law. It's very, very classic. I would be surprised if midterm 2 does not have Ampere's law on it, if I were a betting man. So I would, make sure that you spend enough time on it and you kind of go through different types of problems and different current distributions and in other words, different shapes, so that you know how to apply your contour, evaluate B dot dl, and set it equal to mu naught I encircled. All right, so that wraps up magnetism. Okay, so again, by design, we did it over 2 weeks so that we could truly mark a break between the part of magnetism where we are only focused on finding the magnetic force on a current or a moving charge versus the part of magnetism where our job is to find the magnetic field based on a current, which overwhelmingly is going to be done with Ampere's law, but could also be done with Biot-Savart. Biot-Savart is more complicated, but it works all the time. So the price you pay is that, okay, it works all the time. Maybe you get a nasty integral at the end. Although typically the ones that we do when we do cover it are very limited, just like the ring of current like this. It's pretty straightforward to compute it. So with that said, as always, thank you for watching. Some of you got their midterms back, and so I'll email you in a second. We can talk about it and what to do next. So the average of the lecture was pretty low, at least for Speleo, and it's pretty low by anybody's standard. I mean, you're usually not used to seeing grades that low. I would say just try to just use the data, right? Look at the mean, look at the standard deviation, look at where you're at. If the mean's 29 out of 75, it doesn't mean anything, right? I mean, what matters is how everybody sits relative to the mean and the standard deviations. So that's all that matters. As far as So a few of you have asked me if you should emergency drop. I'm always in the camp of don't. Stay as long as you can through this thing, because, maybe midterm 2 goes a lot better, and, okay, you get a good enough grade in the end that you're not in love with your grade maybe, but you're done with physics. So that's nice. Especially if you have other stuff to do, like, if you're pre-med or pre-dental or whatever, and you're going into that, I know you want a good grade in physics, and I get it, and you should get the best grade you can, but the reality is that you have a lot of other things to do that are very meaningful. And as much as I enjoy teaching physics, I'm also a strong proponent of you getting out of 8A and 8B as quickly as possible. So obviously it's never up to me, it's up to you. Just, don't emotionally react to a bad grade on midterm 1 just because, once you emergency drop, that's it, you got to take it again. And we have the same folks teaching next spring, so it's not necessarily going to change anything, right? So just give it some thought, see what's up, and I'll talk to the few of you that wanted advice. And keep in mind that midterm 2, a couple of things. First of all, midterm 2 will be there before we know it. That sounds obvious, but just, we're at the point in the semester where everything accelerates. And midterm 2, typically, as a class, the lecturer does worse than midterm 1. That's pretty common. The reasons are magnetism and induction. Those are the 2 chapters that are pretty hard, and magnetism shows up right after midterm 1, and you kind of fly through it. And part of the reason is that the excuse is that, oh, well, a lot of this we saw in electric fields, so, it'll help you learn this faster, which I disagree with that logic, but whatever. Point is, you usually fly through magnetism, and then induction isn't much easier either. It's pretty abstract. And those are kind of I would argue, in the top 3 hardest chapters in the whole semester, there's electric potential, magnetism, and induction, I think. After that, it gets a lot better. That's also something to keep in mind. So after induction, we have EM waves, we have optics. That's really straightforward in comparison, incredibly straightforward in comparison. Interference and diffraction, you're never going to really understand conceptually what's going on, probably, but it doesn't matter. You can probably still do the problems because it's very much plug and chug. And quantum is quantum. Nobody understands quantum, and you just do damage control on that one. But it's conceptually the harder ones are the magnetism and induction. So anyway, something to keep in mind. I'm not trying to discourage you, quite the contrary. I'm saying that maybe you can do better than the rest on midterm 2 because nobody's going to like it. So anyway, with all that said, thank you for watching. Thank you for your questions and for chiming in. Always good to hear from you. And I will see you next week. Next week we will move on to induction. That will just be, we'll do it in one live stream because there's no RL circuits. So it's really just Faraday's law and Lenz's law, and that's all it is. So we'll do it in one fell swoop, and then we'll move on to EM waves the following week, which will bring us kind of up to speed with what's going to be on midterm 2 anyway. All right, have a good rest of your week, and I will see you about a week from now. Take care.